myself Shweta Shah. I am an institute for the subject Computer Organization and Architecture. In this subject we have started unit 6, that is pipelining and vector processing. In this unit we are going to see today the topic, that is vector processing. So let me start with the topic. There is class of a computational problem that are beyond the capabilities of your conventional computer. These problems are characterized by the fact that they requires a vast number of computations that will take the conventional computer days or even weeks to complete. Okay, in many science and engineering applications, the problems can be formulated in terms of vectors and matrices, and that lend themselves to a vector processing. For example, long-range weather forecasting, petroleum exploration, seismic data analysis, medical diagnosis, artificial intelligences, mapping of human genomes, or you can say human genome engineering. All of these tasks will require large number of data to be processed, and for that you can use this vector processing concept. Without sophisticated computers, many of the required computations cannot be completed within the reasonable amount of time. To achieve the required level of high performance, it is necessary to utilize the fastest and the most reliable hardware and apply the innovative procedure from the vector and parallel processing technique. So we can complete the task faster. Many scientific problems require arithmetic operations on large arrays of the number. These numbers are usually formulated as a number, as a vector, and a matrices of a floating point number. A vector is the ordered set of a one-dimensional array of data items. A vector v of length n is represented as a row vector by v is equals to v1, v2, v3 up to vn. It may be represented as a column vector if your data items are listed in a column manner. A conventional sequential computer is capable of processing operands one at a time. Consequently, operations on a vector must be broken down into single computations with subscript variable. The element vi of vector v is written as a vi, and the index I refers to the memory address and the register where the number is stored. So we can represent vectors like this way, and this can be your m cross n vector also. A computer capable of vector processing eliminates the overhead associated with the time it takes to fetch and execute the instruction in the program loop, and it allows the operation to be specified with a single vector instruction of the form, like for example, if we have an task like C 1 to 100 is equals to A 1 to 100 plus B 1 to 100. That A, B and C are your vectors, that are your row vector that is having 100 data, and that you require to do addition operation. So for normal operation, what you will do? You will use the loop in construct. You will construct the loop and do the addition and store each and every times addition into your resultant place. In vector processing, we can do all of this task by using simple one instruction. Okay, in vector instruction, it includes the initial address of your operand and the length of your vector and operation to be performed, all in compositing in a one instruction. A possible instruction format for the vector instruction can be given like this: operation code, that is your operation that you require to be performed on the set of this data. Base address source 1, that is starting address of your source 1. Base address source 2, that is starting address of your source 2. Base address of your destination, that means where from which location onwards you are going to be storing your result, and your vector length, that is how many number of data are there in this your vector. So by providing this simple one instruction, you can perform this 100 times addition. Instead of doing this, if you are using the loop, then this task is performed in CPU for 100 times by using this looping concept. Okay, and in this vector processing, by simply using just one instruction, you can complete this task. Okay. Another example we can take for this vector processing is a matrix multiplication. The matrix multiplication is one of the most computational intensive operation performed in a computer with a vector processor. The multiplication of a 2n cross n matrix is consist of 2n raised to 2 inner products and n raised to 3 multiply and add operation. Okay, so total operation will be like n raised to 3. If an m cross n matrix is of number has n rows and m columns and may be considered as a constituting a set of n row vectors and set of n column vectors. Consider the example of a multiplication of 2 3 cross 3 matrices A and B, as we have given like this. A is as A11, A12, A13 and so on represented. A matrices and B matrices are multiplied and result is stored into C matrices. So we can do the product of this matrix C as a 3 cross 3 matrix whose elements are related to the element of A and B, but in the product we can represent Cij is equals to Aik multiplied by Bkj, and that multiplication terms are added for 3 times. Okay. For if we consider for a first column and first row, then I is 1 and j is 1, so we can represent it like A11 is equals to A11 B11 plus A12 B21 plus A13 B31. So simply for one term we require 3 times multiplication and 1 time addition. Okay, so and if we are doing by means of successive addition, then we will require to do addition task for 3 times. First we will make C as empty, then we will first add A1 B1, A11 B11, then we will add A12 B21 and then we will add in this A13 B31. So if we consider the successive addition method, then the number of addition will be more. This requires 3 multiplication and 3 addition, as we have discussed this thing, and the total number of multiplication or addition required to complete the matrix product is equals to 9 cross 3. That means we will require total 27 add or multiplication operation to complete this simple multiplication of 2 matrices. We consider the linked multiply add operation C plus A into B as a cumulative operation. The product of 2 n cross n matrices have a n raised to 3 multiply and add operations. The computation consists of n raised to 2 inner product, and each inner product is requiring n raised to 3 multiply and add operation, assuming that C is initialized to 0 before computing each element in this matrices. So in general, we can consider this inner product is consisting of sum of k products terms of form, and this k can be 100 or 1000. Okay, so let me see how we can do this operation by means of the vector processing. The inner product calculation of a pipeline vector processor is shown over here in this figure. There is source A, source B, then we are using the multiplier pipelining of 4 steps, and then we are using the adder pipelining of 4 steps. And the adder is having 2 terms. One is from output of the multiplier pipeline and another is from adder pipeline's output. So the floating point multiplier pipelining and the floating point adder pipeline are assumed to have 4 segments in each. All segment resistors in the multiplier and adder are initialized to 0. Therefore, the output of the adder is a 0 for the first 8 cycle until the both pipes are full. AI and BI pairs are brought in and all multipliers at the rate of 1 pair per cycle. After the first 4 cycles, the product begins to be added to the output of the adder. During the next 4 cycles, 0 is added to the products entering the adder pipeline. At the end of the 8th cycle, the first 4 products A1, B1 to A4, B4 are in a 4 adder segment, and the next 4 products A5, B5 to A8, B8 are in the multiplier segment. So A1, B1 up to A4, B4 are in an adder pipeline, and A8, B8 to A5, B5 are in a multiplier pipeline. At the beginning of the 9th cycle, the output of the adder is a A1B1 and the output of the multiplier is A5B5, and that is going to be added at this stage and going to be stored into adder pipeline. Thus, the 9th cycle starts with the addition of A1B1 plus A5B5 in the adder pipeline. At the 10th cycle, the addition of the A2B2 plus A6B6 is done, and so on. This pattern breaks down the summation into 4 sections as shown, like A1B1 plus A5B5 plus A9B9 plus A13B13. Second segment will have a A2B2 plus A6B6 plus A10B10 plus A14B14 and so on. So by end of this we will have this kind of addition term. When there are no more product terms to be added, the system inserts 4 0 into the multiplier pipelining, and the adder pipelining will then have one partial product in each of the 4 segments and corresponding to the 4 sums listed in a 4 row in the above equation. The 4 partial sums are then added into form of a final summation. So by this way we can use the vector method to multiply the matrices. So we are ending our today's session over here. If you have any query, then you can contact me.